Okay, I think we'll get started. So today we're going to investigate the shift register, in particular the 74HC595, which is a very popular shift register that is of the form serial in, parallel out. And so what that means is we put our data in serial fashion, and then we release those data in parallel fashion. So the input pins are loaded one at a time, and then the output pins, all 8 output pins are given all at once. I would say arguably the 74HC595 IC chip is probably the most commonly used serial in, parallel out shift register. Now there are other formats of shift registers. I'm not going to go into the real theory of shift registers. There's lots of YouTube videos out there, and if you want to get deeper into those, I would encourage you to spend a little time watching some of those. For us, we're working with this, and I'll just give you a layout of the chip, and then we'll talk about how we'll interface that with the LuckFox. Basically, what we want to be able to do is type in ones and zeros as a user, and then have them show up in an array of LEDs. All right, so we will the output. There's 8 outputs, and these are labeled here in blue as Q0 through Q7. So these are going to be 5 volts or 0 volts, depending on whether we're a true or a false or a high or a low on these pins. The VCC and the ground are in opposite corners here, as is typical, and we're going to be using 5 volts. I think it probably runs on 3.3. I guess I always use 5 volts here. I'd have to check the data sheet to see how low, but I think it does run on 3.3 volts. There are some other important pins. The DS pin is how we load the data we want to go in. So each datum comes in, we want high or low, and that's going to come in a serial fashion. So a high or a low is presented here. Then there's a shift register clock, and as that goes down, I think down, or anyway, as it changes, then this datum gets shifted over 1 in the register, and then we're ready to place the next datum of our choice, high or low, on the DS pin, and then this clocks over, and once we fill the whole register, then we have the storage register pin clock go. And then there's one last thing, is we need the output enable pin to be active in order for these to get their voltages. And usually what we do then is we keep that hidden from the user, or hidden from the output. We keep this pulled high. It's active low, so we pull it high, and nothing comes to the pins until this is pushed low. And so this set of 4 pins are needed to actually load the data appropriately. The other thing about clock is this always kind of throws me, the word clock, because when a clock, I usually think of a continuous pattern, like coming out of a continuous square wave, for example, coming out of a 555 timer or something like that. Clock just means how we're controlling the shifting over. And so in the case of one register, we would click that 8 times to fill all of the outputs. If we click it only 4 times, we've only filled it half full. If we click it 12 times, we've pushed our data off of the chip. Well, where does it go off of the chip? Well, it comes out of this Q7 prime pin, which is a neat feature about these shift registers, is that this guy then can be put as the DS pin on another shift register. And that's what we're going to do. We're going to see these daisy chained. We're going to have 10 LEDs, so that's more than what we can handle with the 8. So we're going to need a second register. We're not going to need the full register, just 2 outputs. So we're going to clock in 10, really 16, because we're going to fill with a buffer of zeros, but 10 meaningful data into 2 of these chips to light up 10 LEDs in the pattern that we would like. Okay, so how are these going to be connected to the LuckFox then? I've just decided to use pins 52 through 55, those 4 pins. You can use whatever you want. These are just a nice collection of pins here. So they'll be assigned this way, and they're assigned this way in the software. And then there's this master reset, which in many cases you don't really use. You just set that to high because you don't want to be resetting the chip all the time. And then we don't need to interface the LuckFox with the other shift register, other than we just run a wire from, say, the input here, say here, we just run that to the same pin on the register. So we're not taking up additional pins no matter how many more 595s we put daisy chained in. So we pay a price of 4 pins. We get 8 pins per register after that. Okay, well, if you're just chugging along through the series, then you're all good. You're all set up with your LuckFox. If you've just come to this video new and you haven't really set up your LuckFox for what we're doing here, then I would encourage you to look at the LuckFox tutorial, and in conjunction with that, there's a really good video by Fusion Automate where he sets up the LuckFox with the Ubuntu Linux operating system, which is what we're doing and writing our code in, and or just running the LuckFox on, and then we run Python in that. We've set up Python earlier in the series, so you can go back and consult that. And as I mentioned, tons of videos, good videos on how the shift registers work. So if you're interested in that, you should follow up on that. All right, so let's get to the computer and start tackling this problem. Let's first look at the circuitry, and we'll just kind of go through things. So this is the LuckFox. Here are the pins 52 through 55, and they're going into the 595, and it's kind of obscured here by all these wires. Here are 3 just open chips that we're going to use later, not in this experiment, but in this special project. But I thought I'd leave them here so you can see the full bare chip, not covered with wires. These top 2 are daisy chained. We're going to use all 8 of these outputs, and we're going to use 2 of these outputs here. These 2 wires on the LuckFox are just the system bus right here. That's, in my case, I'm getting 4.9 volts, so basically the 5 volts, and then the ground pin here. We need to make sure that we use the same sources of power for the chip and the LuckFox, so we're not floating one relative to the other. Okay, then again, kind of a big rat's nest here, but each of this bundle of orange wires, there's 8 of them, 7 down this side, and then 1 across here. Those are going to be Q0 over here, and then Q1 through 7 down the side. There's a ground pin here that we can't really see. We can see it better here with this green wire going to ground on this second chip. Same thing is happening up here. And then there is a wire going from the 5 volts to the top pin 16 on this 555. So that's powering everything. The pins 55 through 52 are coming in over here as the data pin, the shift pin, the storage pin, clock pin, and the output enable pin. Then there's a wire here. It's hard to see. It's kind of obscured, but there's a wire going from the Q7 prime to the DS pin on this guy. And then the pins here, just Q1 and or Q0 and Q1 coming out of here. And I think for the output pins, if they're okay to float those, at least I'm not having any trouble at all. It makes sense that they'd be okay to float. The input pins you definitely don't want to float. You want to make sure that the ground is to the same ground. The master reset is pulled up to the same up voltage, and all these pins are connected, and everything should work fine. All right, I've got this fancy 10 bin LED bank. It's a pretty cool LED bank. You can certainly just use regular LEDs. Now, a little bit of a confusing thing here that I want to alert you to. I have connected these to the 5 volts rather than to the ground. So this is going to put the LEDs in active low configuration. So we're going to, it'll be a little confusing. When we put our pins high, then we won't get a light up. When we put a pin low, we will get a light up. So in our code, we're going to have to invert that, and I'll mention that when we get to the code. So we want to put in a 1, we want to type in a 1, we type in a 0, we want those to be on and off. It makes more sense that way. But in the setup here, it would be inverted because I've got my resistor here attached to the 5 volts. It probably doesn't matter. My understanding is that one advantage of doing this active low configuration is that then you're running it to ground on the 555 chip rather than having the chip run from its 5 to the base ground, which apparently is a little better setup. But I'm certainly not an expert on that, and I think it probably would work the other way as well, the more sort of natural way, so that when your pin is high, your LED is high. So we're going to have to take some of the software to flip that to make it make sense. All right, so what we're really seeing here then is just 10 resistors hooked to the 5 volt, then to this LED bank, and then to the output pins. And again, if the output pin is low, then we have a 5 volt to ground, so the LED will light up. If the output pin is high, then we have 5 volt to 5 volts. The LED will not light up. Okay, so I'm going to move my camera back over here. Let's take a look now at, just very quickly, the 595, sorry, I just got that from DigiKey. I think you can get it other places. Relatively inexpensive. I mean, not super inexpensive, but $1.26 a pop. And you might want to have a few of those in your repertoire. They're one of the classic shift registers. And then this fancy LED. This is pretty handy, so you're not having to plug in all the LEDs. I want to get a resistor bank too, so you just have a chip here that you hook up instead of having to put the individual resistors in as well. But even with this, this is going to be handy. And we are going to actually use this fact that they can, if you put another one right next to it, it'll make just a nice long chain in our special project later in the course. And relatively cheap, obviously a lot more expensive than an LED or even 10 LEDs, but very, very handy in its setup. Okay, so these are those two extra pieces besides the LuckFox. And then finally we'll go to the LuckFox pinout diagram. And so we're using the system bus and the ground. Those are the pins we're using to power the whole setup. And then over here we have pins 55 through 52 here as being the operational pins here that are going into the 595. Okay, well, not too much left to do. So there isn't any special Python packages or anything. We're just going to use periphery. So let's go get the code and then get that into the LuckFox and run it. So to get the code, you can just go to our LuckFox page. So if you go to my website here and then teaching LuckFox. Let's scroll all the way down to the bottom here. We're going to be using the 74HC595.txt. Again, text, I have this as a text, it's actually a Python file. So let's open that up. And I'll grab this first. We'll put it in to our LuckFox, and then I'll explain it a little bit. Okay, so I'm over in the LuckFox now, logged into LuckFox. I made that directory, projects directory, to just put all my Python files. You can do this wherever you would like. So let's just make a file called 74HC595.py. Oops. Can't just say that. I got to go sudo nano and then our file name here. This will open up the editor once we put our password in. And I'll just paste in, so just right click and paste in the code. Now let's walk through this code a little bit. So periphery is all we need. That will set up the GPIO, that'll be bring in the package that allow us to set up the GPIOs. Pin is just for timing stuff. So we are going to need that, time is just for timing stuff. So we'll import time here. Okay, this is just defining, giving names to the pins. We could just call this 50, 53, 52, 54, etc. So data pin, shift clock pin, latch pin, and then the output enable pin. And then we initialize the GPIO pins with sort of the standard periphery stuff that you would use even on a Pico or anything else. Okay, now we are going to define a couple of functions here. We need to pulse in, so we're essentially bit banging these in. So we're just turning on and off our GPIO pins. We're not sending it via UART or I2C or anything like that. It's just direct communication of the pins. And so this is just a pulsar. So it writes true means 1, and then false means 0 to the pin. So it's just up and down here with this pulse. And then there's a function here, shift, for pulsing the latch pin. So to shift that in, so we shift the clock 8 bits, and then we shift the latch. Then I said 8 bits. Actually, we're going to do 16 bits because we have to fill 2 full registers. Then this little function here, this is because of the way I wired the LEDs to be active low. So you wouldn't use an invert. You wouldn't invert for this, but all this function here is going to do is invert the numbers, so that when we as a user type in a 1, it will result in the LED being on. So we want that to be, that's more natural. So we want that to be true. Then here is the function. So it's going to ask us to enter a 10-bit binary number, so 1s and 0s, and we want that to show up on our LEDs as on and offs. And we do need a couple of things here. We call the invert function, and then notice here we need to fill all 8 pins on both registers. So we need 18 or 16. So we're only giving 10 numbers. So we have to buffer this. We have to concatenate with just a bunch of zeros or ones. It doesn't matter, but just a bunch of zeros in this case, so that we get the last 10 digits to be what we are wanting. So the first 6 digits are zeros, and then the last 10 digits will show up as lit up LEDs. Okay, so that's kind of it. So we'll save that, and then we will go sudo python 3 and it's asking for a binary number. So let's give it all ones. That should turn everything on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we look at our, where's my pen here? Well, we look at our LEDs. They're all 10 of them are on. Let's go ahead and give it all zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. Hit enter. They're all off. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now we'll orient ourselves. We couldn't yet tell which is up and which is down. So we've written this. So this should be, the lead digits should be here. So when we turn this on, the ones are here and then the zeros are here. So this is our lead digit in what we write. So that's this digit here. And then this digit here is the top one. So if we go 0, there's 1, 2, 3, 4, 5, 6, 7, 8, and 0. Oop, didn't do enough. 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we've turned on and off the top, the top and the bottom. And then we'll just do one last one. So 2, 4, 6, 8, 10. So this will be alternating with the green on the bottom. And so this value is pin 1, Q1 of the second register. Q0, remember, starts counting at 0. And then this pin here, or this value, is output pin Q0 on the first register. All right, so that's the shift register. As I mentioned, this is used to increase the number of outputs. So here we got 10 outputs for the cost of 4. And as we daisy chain more and more, we're only ever using 4 output pins on the LuckFox, and we're using gaining 8 output pins every time we add another 595. So our project coming up, I'm gonna try to get it to work with 40 LEDs, maybe 80, but 40 for sure. And so we'll use a whole bunch of these. That would be more output pins than the LuckFox itself has. Of course, with 10, there are 10 available GPIO pins on the LuckFox, so you could do it with the LuckFox alone. But the purpose of this lab was to get us to work with this really important shift register and see the potential for more pins. All right, that's it for the 74HC595 shift register.